All right, so let's let's walk this one through. So we need to bypass the register file, recirculate these values from the ALU. So we need to modify the expressions for source value. So here are my original source value expressions. And I want to see if the previous cycle we had a write to the register file. So previously RF write was enabled, and my source, so this would be SR1, RS1. It's my source index is equal to the previous instructions destination register. You guys can check me. Let me know if I'm making a mistake here. And, well, write enable takes care of that. So if we write the register file, I suppose I'll just use, it should work this way, but let's literally take what was written to the register file. So that would be the RF write index. Feels like it should be more than that, but I think that's it. It should be a ternary, right? If I need to bypass, then take the previous values, write data, write, no, yes. Okay. Look right to you guys. Did I make any mistakes? If I made a mistake, you're all to blame. All right, let's do the second one as well. Right. I did make a mistake. You didn't catch me. Is it write enable 1? Write enable 2? Source 2, my source 2 is equal to the previous instructions write index. Right. Okay, so hopefully that's my register file bypass mux. And we're in stage 2, that's correct. Source values like previous result. Okay, so I coded this up to use the register file write data. Should be the same if we're using result. If RD is the previous register source, again, I directly use what we're actually doing to the register file, but register source should do the same. So that should be 2, and make sure taken branch logic uses the bypass value. So my taken branch logic, here's my taken branch logic. I'm using the source 1 value, which has the bypass in it. Okay. Any questions about this lab? Everyone got it? Let me compile and check my behavior here. write enable is used but never assigned. Let's see. So the RF write, oh, okay. Oh, I was right the first time. 234. Thank you. Let's try that. Log looks clean. Let's check our behavior here. Looks good. Okay, next lab. So we took care of the register file write. All set there. Next is our branches, right? So branch, we literally don't know our target, and if we're taken, more importantly, if we're taken, the target we actually know a little bit earlier. But we haven't determined whether we're taking until stage 3. So the best we can hope for, if there is a taken branch, and at this point we're not doing, and in fact for the whole course, we're not going to do any kind of branch prediction. So our default behavior for branches, just like every instruction, is to fetch to the next sequential instruction. So if we do have a taken branch, the best we can hope for is this, you know, a 3-cycle dependency. So the intervening instructions are marching through the pipeline, doing their thing, but we need to make sure that they don't cause any harm once we figure out that we have a branch. Right, so fortunately in our CPU pipeline, we're not writing any architectural state any earlier than stage 3. So when we find out that we have a branch, we need to mark these guys invalid. By marking them invalid, we'll cut off the register file write, and they will do the proper redirect to the proper PC. Okay, so the waterfall diagram now for a loop, or for a branch rather. The branch is going to branch to a target. If it's taken, these 2 intervening instructions get squashed. We squash their register writes. Well, we squash the instruction and register writes. And begin fetching again. So to address this, we need to determine that the instruction is valid based on whether we're in the shadow of a branch, right? The shadow being those 2 instructions that we have to squash. So previously, we were just regularly doing an instruction every 3 cycles. We had this valid logic set up. Now that we're trying to execute instructions every cycle, we're going to get rid of this valid logic and replace it with valid logic that's based on the branch. Okay, we need to know valid in time to squash the register file write. We don't need it any earlier than that. So here, when we determine is taken branch, we determine I guess we have an extra cycle here. Okay, yeah, I have depicted this right. So whether we are valid depends on the previous instruction being a branch and instruction before that being a branch, right? So we are a taken branch, and that affects the next instruction and the next instruction after that, forcing them to be invalid, squashing their write. Okay, so this old code that we had for valid and start, you can remove and create a new assignment for valid to take its place. It's going to assert as long as there is not a valid taken branch in either of the previous two, either of the two instructions ahead of us. And then we're going to, now that we're executing instructions every cycle, for the most part, we're no longer doing the increment every third cycle. We'll go back to doing the increment every cycle. Right, the branch, when we redirect the branch, that is a 3-cycle dependency, so that one stays as it was. Any questions about this? Right, so again, this is giving us this picture. We're going to fetch instructions every cycle because we're redefining valid. We're going to increment the PC every cycle. And we're going to squash instructions in the shadow of a branch. Make sense? All right, go to it. All right, so I'm going to see what I can do with this. I'm going to get rid of my start assignment and my old valid assignment. Now I'm going to assign those in stage 3. And I'm going to be valid. As long as I'm not in the shadow of a valid taken branch. And I also don't want to be valid if we're in reset. And then I want to increase and increment the PC every cycle. That's that. Still, the branch is a 3-cycle window. And that should be good. So I'm executing instructions every cycle. Branch has a 2-cycle shadow. And I'm getting 45 and stopping. So looks good. Anybody need some additional help? The PC mux? Okay, so the valid expression here. So we're going to be valid as long as we're not in reset and we're not in the shadow of a branch. So we're not in reset and we're not in the shadow of a branch. So we're in the shadow of a branch if we have a taken branch, the instruction before or the instruction before that. So the instruction that's ahead of us or ahead of that. Maybe I should make this a little bigger. Dr. Bopu, when's the break? Okay. So 15 more minutes, that'll give us time for this one. So now that we have our, our basic test working, we have our CPU pipelined, we have all the logic updated to support that. Let's go back and complete the CPU for the remaining instructions. So that means completing the instruction decode to break down all the instructions, and what else? And the execution unit to execute all those instructions, the ALU. So let's start with the instruction decode. So back to this table, you've already taken care of the red circled instructions. So go back now and add all the remaining instructions to the, to the is instruction signals. A couple things to note. Since our CPU is not going to support the byte granular memory operations, there are a bunch of memory instructions that are not operating on a full 32 bits, so either on the 16-bit or an 8-bit quantity. We have load byte, load half, and then load word. We're supporting load word behavior, and then there's load byte unaligned, load half unaligned, which affects in those cases, you're loading a small value into a 32-bit value, so what do you do with the upper bits? So we are going to treat all 5 of these flavors of load as load word. So just create a isLoad signal to decode all of these the same way. And similarly, stores, there's store byte, store half, store word. We're going to treat all of those like store word. We already have a signal that distinguishes these. All the store instructions are the same instruction type. They're all S-type. So what's my suggestion here? So my suggestion for stores is not to bother decoding them. We'll just use the is-S instruction to be is-store. I think that's it. So go ahead and go through this whole table. Okay, if you don't have all the instructions coded yet, just try to make your code, get your code to a state where it will compile, and you can always go back and fill in the remaining instructions later. So I've cheated. I've just gone to the reference solutions and cut and pasted. But this is my block of code. Okay, so we know what the instruction is now. Now we need the arithmetic logic unit to actually act on that instruction appropriately, do the right computation. This table shows all the remaining instructions and what their operation is. So I'm not going to ask you to come up with the logic expressions for each operation. I've just spelled that out here. But you can go through and add to the ALU all of the cases for these instructions and the corresponding computation. The only real wrinkle here is that SLT and SLTI share a common sub-expression from SLTU and SLTIU. So this is the unsigned and signed versions of the Yeah, something like that, the signed and unsigned versions of the instructions. So I would recommend pulling these these comparisons out as separate signals, and then you can use those signals here in these expressions. Basically, I had to do that just so I could fit this on the slide. But that's what's meant here is this you can assign to SLTU result, and then use SLT result here and for SLTU, and same for SLTIU result. Okay, but otherwise it's just going through. Okay. So I have my two common sub-expressions here for SLTU and SLTIU, and then I'm using those down here and here, and here and here. Otherwise, it's just, copying all these expressions for the various cases. If we're in add I instruction, we're doing and I instruction, we're doing the and, etc. So I don't think there are any surprises here. One thing I did forget to mention is that for these expressions, I'm taking advantage of the automatic width extensions. We have checking enabled, so we're going to see warnings if we have width mismatches. So the next lab is just to silence all the warnings that we see in the log, right? If you look in the log, it's very noisy at this point with all kinds of width mismatches. That seems excessive. I don't know why there are quite so many, but for example, the XOR operator produces 1 bit. This is a, actually that's not true. Well, which one's complaining? So the SLT, this sub-expression here, for example, that's a comparison. It produces 1 bit. The instruction result should be, a 1 or a 0 in the low bit, and the rest of the bits should be 0. And I'm just letting Verilog's rules do that for me. But the width checking is enabled, so we're getting warnings for all those cases. So let's just clean that up. We'll keep the simple expressions, but let's, state that in this region of code, don't report warnings for these. And this is how you do that for Verilator specifically. So I'll just do this along with you. So use this. Around these expressions. And then at the bottom, instead of off, it's on. Oh, okay. So the note here is that this is what you see in the log. The log is telling you to use these if you want to quiet down the messages, right? Looking in the log. At the bottom here, use Verilator lint off width expand to quiet this down. We actually want to use width instead of width expand. So let me correct that. And that should be it. Let's compile. And we now see a clean log. I'll just leave that up for a second. Okay, so our CPU is working, it's pipelined. We have two things remaining, I believe. First of all, our CPU has no memory. Our test program is operating completely out of registers. So next is to add support for loads and stores. And we are also currently missing support for jump instructions. So starting with loads and stores, we have various flavors of loads. As I mentioned before, we're only going to support load word. Loads are formatted like this. Go full. So loads are formatted like this. This is the destination, so this is the value that's being loaded from memory. The load data is written into RD, and they have an immediate and a source register that specifies the address. So the address that we're loading is the RS1 register plus the immediate, which is signed. So the address is RS1 plus immediate, and RD is loaded with the memory address. Stores have a source register that provides the data, and similarly an address given by a register and an offset. And we're updating memory, opposite of loads, to contain that value. So words, half words, bytes, but again, our CPU is just words. So in our CPU, the data memory will live here. The data that we need to write is coming out of the register file. So it's the RS2 value, which will be here. We need to tap into that on the output of our bypass mux in case the previous instruction is writing RS2, right? So we tap in here, that's our data that we're going to write. The address that we're going to write is RS1 plus immediate. That happens to be the same operation as add I, okay? So for load and store instructions, we're going to use the ALU to do the same operation that it would do for add I and use that as our store address. Okay. Similarly, it's common to share the ALU with other operations, the branch comparison, right? You might use the ALU to compute that. The comparison has some similarity with other instructions that you might be able to share logic. Okay, so the load data then is going to pop out, and we'll deal with that later. But for now, we're going to drop the memory in place and hook it up. So the lab to do that, well, before we get to the lab, so just looking at this in our waterfall diagram, right? We have a load. The load data is going to come back in stage 5. So that's this path here, right? So the load is determining the inputs to the memory in the execute stage from the ALU, and we get the data back here. So to satisfy this, we need to be able to write the register file when the data comes back 2 cycles after it would normally be available for an ALU operation. So since it's coming back 2 cycles later, we need to be able to write the register file. We can't be doing anything else then. There are various ways to handle this better, meaning with better performance. We're going to take a reasonably simple approach. We're going to take exactly the same approach that we took with the branch instructions and simply squash the instructions in the shadow of the load. So anytime we have a load, just like we do for a taken branch, we're going to squash these 2 instructions, and then we're able to write the data back into the register file 2 cycles later when it comes back. So same thing, but in our waterfall diagram, so we can see more details of the logic. ALU sends the address off to memory, and the data sent to the memory comes back with a 2-cycle delay. That's when we write the register file. We squash these two instructions, A, because they might be dependent on the data coming back from the load, and B, so we can free up the slot to write into the register file. And then we continue execution. So the first step is to implement the redirect. So we've already done a similar redirect for taken branches. This will look similar. So we have this valid logic that is considering the shadow currently of the taken branches. We want to factor into this logic also load instructions. So if the previous instruction was a load or the previous instruction was a load, we're invalid. A valid load, I should say, right? If the previous instruction was a valid load or the one before that was a valid load, we want to squash this instruction. And then just like we do for taken branches, we want to update the PC. In this case, the correct PC to follow the load is the next sequential. So it's the loads PC plus 1. Plus 1 just like all instructions, except the load, we're doing the next instruction 3 cycles later. So if we are if the instruction, if the instruction that's ahead of us by 3 is a load, our PC is its PC plus 1 instruction. Okay, so the first step is to factor in validity to create the shadow of the load. And the second step is to correctly assign the PC for the instruction that's following the load, which has been delayed 2 cycles. Okay, so think that through, update the valid logic, update the PC mux, and then I'll walk through it. Again, refer to these earlier slides if you need to understand what we're trying to accomplish. This one through together, and then we'll wrap up for today. So step 1 here is to update the valid to consider the shadow of a taken load. And I think I'm going to update my slide here to, not a taken load, a valid load. I'll update my slide to reflect that. So I need to find my valid expression, which is here. I've got my reset case, and I've got the shadow of my taken branch. And I need to also factor in valid loads. So I haven't defined valid load yet, but I will. Here's valid taken branch. Let's do the same for loads. So I believe I have an isLoad. Let's see. There it is. Okay, so that should take care of creating the valid, the shadow of the load, right? That should invalidate these 2 instructions. So again, this is adding a term for to clear valid if the previous instruction was a valid load or the previous was a valid load. So that's this, part one. Part two is incrementing the PC properly. So for this scenario where where I'm updating the PC for this instruction, if this instruction was a valid load, then this instruction should be the instruction immediately following this instruction, right? So what's happening in the machine is, say this is a load, this instruction would be the instruction immediately following the load, the PC plus 1 instruction. This would be PC plus 2 instructions, and then they get squashed, and I have to redo this one. Okay, so I've squashed it because it might not have the register available from the load. I need to squash this so I can write the register coming back from memory. Once they're squashed, I need to re-execute this one. So the PC for this guy is this guy's next PC, incremented PC. So in my PC mux up here, I have my similar case for take and branch. Now let's do valid load. So for this PC update, if this guy was a valid load, I need to use his incremented PC. Right, so that's giving me this red path. If this guy, for this guy, if this guy was a load, take his incremented PC as my PC. So let's run this. I don't think there are any loads in our test program, but let's at least make sure we haven't broken anything horribly. So it looks like I'm still getting 45. Any questions about that? Yeah. Let's see. So my expression's inverted. Let's look for valid. So I could also drop this in here, right? You've heard of De Morgan, right? When you invert the expression, the ors become ands. Yeah. So I believe those two are the same, unless I goofed. Any other questions? Okay. So tomorrow when we come in, we will finish up memory. We'll instantiate the memory. Thank you. On Monday when we come in, we'll instantiate the memory and deal with the load data. And then we'll add a load and a store to the program just as a sanity check. And then the only thing remaining will be jumps. Okay, so we should be, able to finish our CPUs, probably within 2 hours on Monday. All right. So just to review what we did today, right? Today was all about pipelining. Yeah, question? So looking at our pipeline, so why is the data memory not in the third stage? So it all depends on the timing of the signal, right? I mean, in reality, a memory access could be a 200 cycle operation, depending where you have to go to find the data. Um, we're assuming a very simple model, but it's all a question of what your assumptions are. How long does it actually take to go out to memory and get the data back? So, today was all about pipelining the CPU. I mean, I think just looking at the picture of where we ended is probably the most significant thing. Um, it was all about these two hazard scenarios, right? So we stretched out the logic, fine. The only two issues that remain are these hazards where now that we're overlapping the execution, there's something that we need from one instruction to feed to the next instruction, but we don't have that information yet, so how do we deal with it? So for the register file, read after write, we dealt with that by bypassing the register file to basically speed up the path from the execution of one instruction to feed into the execution of the next instruction. So you can look at it as bypassing the register file, or you can look at it as register forwarding from the arithmetic logic unit to the input of the arithmetic logic unit. And then we dealt with branches by creating a shadow for the branch, squashing the instructions after the taken branch, and redirecting the PC appropriately, right? And then just now we dealt with the loads, similarly created a branch shadow to give ourselves extra time to get the data back from the load into the register file. All right, almost there. We almost did it in a week, but we'll wrap it up quickly on Monday. And then after that, I have some lecture content on the nature of design teams, how the different roles on the design teams, how the teams work together. We're focused on logic design for all this section of the workshop, the CPU design, but it's not all about logic design. The bulk of the effort is actually the verification. There's a lot of infrastructure around verification to make sure that our CPUs are 100% correct. A lot of this stuff we're not verifying very well at all, and that certainly wouldn't fly in industry. So what are the techniques to really get 99.99999% confidence in the designs that you make? And then there's also methodology around the post-silicon, right? So we're focused on what would be called pre-silicon, where we're designing the thing, then it gets manufactured, turns into actual silicon. You have to make sure the actual silicon is working the way it did in simulation. So we'll talk about all the activities that go on there as well. And after that, it's open project time. So I think we'll probably get to final projects on Tuesday. I have a few things about TL Verilog that I'll probably cover before we, probably cover Tuesday morning or so, as kind of introduction and ideas and so on for the final project. Some additional modeling methodology that we don't need for the CPU that might be relevant for your projects, things like that. But essentially, I think Tuesday through Friday is going to be open projects, which is where you take everything that you learned designing the CPU and get creative with it, right? So I think that's the fun part. So I forget the actual timetable for our submission. We would be on Tiny Tapeout 11, I believe. So 10 has already passed. I know the template for Tiny Tapeout 11 is not yet in place, so I think it's several months out. I think it's maybe 9 months or something between Tiny Tapeouts. So we probably have half a year or so before the submission, but I'd have to check the schedule to be sure. So yeah, I mean, even if you want to make tweaks after the course, you'll have time to do that. Uh-huh. Yeah, so we might be able to check that quickly. Tiny tape out, I believe .com. 84 days. That's not right. That's tiny tape out 10. All right, maybe I'm wrong. Maybe it is tiny tape out 10. Apparently we have 84 days left. All right. Okay, good job this week. See everybody next week. Yeah, it looks like it. I think I had the dates wrong.